Welcome to Data Structures and Algorithms. We are going to learn today some basic terminology regarding data structures and the notations that we would be following in the rest of this course. We'll begin with just some very simple definitions. An algorithm, which is an outline of the steps that a program has to take, right, or any computational procedure has to take. A program, on the other hand, is an implementation of an algorithm. It could be in any programming language. A data structure is the way we need to organize the data so that it can be used effectively by the program. Yeah. So, you all are familiar with certain data structures, an array or a list, for instance. So, this course is about, you will be seeing a lot more data structures in this course, and you will see how to use them in various algorithms. So, we will take a particular problem, try to solve that problem, and in the process develop data structures, the best way of organizing the data associated with that problem. Okay, so what is an algorithmic problem? An algorithmic problem is essentially that you have a certain specification of an input, as is given here, and you specify what the output should be like. And a specification of an input could be, well, here is one specification: a sorted non-decreasing sequence of natural numbers of non-zero finite length, right? That is an input. That is a completely specified input. I have given two examples here of inputs which meet this specification. I have not given any output specification yet here, right? Now, what is an instance? These are two instances of the input, right? This is the specification for the input, and you can have any possible instance. You can take any sequence of sorted non-decreasing numbers, and that would form an input instance. So, there are infinitely many input instances possible here. So, an algorithm is essentially describing the actions that one should take on the input instance to get an output as is desired, as is specified. And again, just as there can be infinitely many input instances, there can be infinitely many algorithms for solving a certain problem. Yeah, each one of you could do it in a slightly different way. So, that brings us to the notion of a good algorithm, right? If there are so many different algorithms for solving a certain problem, what is a good algorithm, right? So, a good algorithm for us is an efficient algorithm. Yeah, anything that is efficient is good. And what is efficient? Efficient is something which has small running time and takes less memory. These will be the two measures of efficiency that we will be working with, right? There could be other measures of efficiency, but these are the only two we would be considering in this course. And most of our time we would be spending with running time, really. Yeah, space, of course, we will also be analyzing the space, but most of the time would be spent in worrying about the running time of our algorithm. And we would be interested in the efficiency of algorithms as a function of the input size. So, clearly you can imagine that if I have a small input, right, and my algorithm running on that input will take, or my program running on that input will take less amount of time. If the input becomes 10 times larger, then the time taken by the program would also grow. Maybe it becomes 10 times, maybe it becomes 20 times, maybe it becomes 100 times, I do not know, right. So, it is this behavior of the increase in the running time with the increase in the size of the input that would also be of interest to us. Okay. So, we will come to all of these in a short while as we go through these slides. Okay. Now, how does one measure running time, right? So, I said efficiency, running time, very important for us. So, how does one measure the running time of an algorithm? So, one way would be to what I have put down here as an experimental study. You have a certain algorithm, you implement that algorithm, which means you write a program in a certain programming language. You run the program with varying data sets, right? So, some smaller, some larger data sets, some would be of some kind, some would be of a different kind. So, varying composition. And then you clock the time that the program takes, right? And clock does not mean that you sit down with a stopwatch. You would perhaps just use a system utility like, let us say, system current time (mls) to clock the time that the program takes. and then from that you try and figure out how good your algorithm is. Yeah, so that's what one would call an experimental study of the algorithm. Okay, now this has certain limitations, so I've put them down. First, you have to implement the algorithm. To be able to determine how good your algorithm is, you have to implement it. Now that's already a huge overhead, right? You have to, a considerable amount of time has to be spent in doing this. Then your experiments can be done only on a limited set of inputs, right? After all, I said the number of instances is infinitely large. You cannot be running, you can only run your experiments on a small set of instances. And that might not really be indicative of the time that your algorithm is taking for other inputs, which you have not considered in your experiments. Further, if you have two algorithms and you have to decide which is better, you have to use exactly the same platforms to do the comparison, right? By platform, I mean both the hardware and the software environments. Yeah, because as you can imagine, different machines would make a difference, not just different machines. In fact, even the users who are working on that system at that particular point would make a difference on the running time of your algorithm, right? So it becomes very messy if you have to do it this way. So what we are going to do as part of this course, and in fact in this very first lecture, is to develop a general methodology which will help us analyze the running time of algorithms. Okay, and we are going to do it as follows. We are going to first develop a high level description of an algorithm, a way of describing an algorithm, and we are going to use this description to figure out the running time and not implement it or any such thing. Our methodology would help us take into account all possible input instances, and it would help us, it will allow us to evaluate the efficiency of the algorithm in a way that is independent of the environment, independent of the platform that we are using. Yeah.
Let's take a short break and just recap what Professor Naveen has covered. So he talked about the problem, input specifications, output specifications, instance, and algorithm. So what is a problem? What are input specifications? What are output specifications? What is an instance? What's the difference between an instance and a problem? And what's an algorithm? Let's try to recap this very quickly. So in this case, our problem is sorting a given list of integers. What's an input specification? It says that my input is a sequence of n numbers that are separated by commas. Okay, and what is my output specification? My output specification says that I need in the output a sequence of n numbers separated by commas. But is that enough? Actually, we need something more in the output. What should the property of the output be such that our problem is solved? Basically, the next number, if you look at any pair of numbers, the next number should be greater than or equal to the previous number. Is that enough, or do we need something else? We need one more condition, which is that the output numbers that you get in the output should be the same as the numbers that you have in the input. In other words, the output is a shuffling or a permutation of the input. Right? So my output specification says that output is a sequence of n numbers which are sorted, which means that the next number is always greater than or equal to the previous number, and output is a permutation of numbers. You cannot have any arbitrary numbers in the output. Whatever numbers you give in the input, the same numbers you have to give in the output, but in a different order. You have to shuffle them such that they become sorted. What is an instance? instance, let's say we are sorting 5 numbers. So my instance 1 could be, or let me write it as, yeah, instance 1 could be 5 numbers like 10, 12, 4, 3, 7. So this could be an instance. It's a list of 5 numbers separated by commas. Another instance could be 7, 9, 32, 100 and 0. Right? But here what we are looking at is n is fixed, but we want n to be not fixed. We want our program to be able to tackle any number of numbers, right? To be able to tackle 5 numbers, 10 numbers, or 15 numbers. So in order to do that, we can modify the input specifications as the number n followed by a sequence of n numbers separated by comma. And in the output I could do the same thing, the number n followed by a sequence of numbers separated by commas. So in this case, how my instances will look like? Let's say instance 1 of size, let's say 4. How could it look like? My first number is the number n, which is 4, and then I have the numbers to be sorted. And so this could be instance 1 of size 4. I can have another instance, instance 2 of size 8. And this could look something like 8, the number n, followed by 8 integers which are comma separated. I can do 1, 2, 7, 9, 6, 8, 0. And one more, let's say minus 7. Right? So this is an instance 2. This is my instance of size 8. What is an algorithm? An algorithm is a step-by-step instructions to solve a given problem. A kind of like a high-level description in a mixture of natural language like English or whatever native language you use and programming language. And this is generally called as a pseudocode. Yeah. Pseudocode, right? So let's go back to Professor Naveen's lecture to see what a pseudocode is and how do we write algorithms in the form of a pseudocode.
Okay, so I said we'll give a high level description of the algorithm, right? This very first point here, we'll give a high level. So what is this? So this brings me to what we'll call pseudocode, and this is how we are going to be specifying all our algorithms, right, for the purposes of this course. Yeah. So here is an example of a pseudocode, and you might have seen this in your earlier courses also. So what is this algorithm doing? This algorithm takes an array A which stores n integers in it, and it's trying to find the maximum element in this array, right? What I have written here is not a program, yeah, because I think the syntax is all wrong, yeah, but it is pseudocode. It is a mixture of natural language and some high level programming constructs. So I'm going to be using, so I'm going to come to all of that, but I'm going to be using like a for do loop, I'm going to use an if then else statement, I'm going to use a while loop, all of that I'll use, right? But I'll not bother about, okay, there should be a semicolon here or there should be a colon here. I'm not going to bother about those. Those are, things that are required by a compiler, but for our understanding this is completely clear what this program is doing, right? So what is this doing? It's keeping track of the maximum in a variable called current max, which is initialized to the first element of the array, yeah, and then it is going to run through the remaining elements of the array, compare them with the current maximum element that we have seen. If the current maximum element that we have is less than the current element, the element under consideration, then it would update current max. AI becomes the new max. Yeah, and then when this loop terminates, we would just return current max. So it's a very simple algorithm, but just with this pseudocode you are able to understand what it is doing. This will not run on any computer, it's pseudocode, but it conveys the ideas, it conveys the concepts. Yeah, any questions till this point? Okay, so that's what I was saying, it's more structured, pseudocode is more structured than usual prose, but it's less formal than a programming language. Yeah, and what will our pseudocode look like? We'll use standard numeric and Boolean expressions in it, right? Instead of the assignment operator, which is equal to in Java, I will use this left arrow. Yeah, and instead of the equality operator, equality relationship in Java, which is 2 equals, the same in C, I will use just a single equal. Yeah, and I'll declare methods in this manner. So name of algorithm name, what are the parameters it takes. I'll use all kinds of programming constructs. So I'll use if then statements, if then else statements, while do, repeat until, for do. To index arrays, I'll say AI, Aij, so on and on. Right? It should be clear what this is doing. And I'll use return when the procedure terminates, and return value will tell me what is the value returned by the particular procedure or a function. And when I have to make a call to a method, I'll specify that with method, name of the method, the argument, and what is the object that it is returning. Any questions to this point?
So what was the object?
This is specifying the type of the value returned by the particular method. You'll see more of this when we come across more pseudocode. Okay, so how do we analyze algorithms? So we identify what are primitive operations in our pseudocode, right? So what is a primitive operation? It's a low level operation. Examples: data movement. I do an assignment from one to another. I do a control statement, which is a branch if then else, a subroutine call, a return, or I do arithmetic operations or logical operations. These are all, we'll call them primitive operations. And in my pseudocode, I just inspect the pseudocode and count the number of primitive operations that are executed by the algorithm. Yeah. Okay, so we need to take an example now. I'll take an example of sorting. You all know what sorting is. Yeah, the input is some sequence of numbers. Output is a permutation of the sequence, which is in non-decreasing order. Okay? So if this were my input, this should be my output. Okay, what are the requirements of the output? We said it should be in non-decreasing order, and it should be a permutation of the input. Any set of numbers which are in non-decreasing order doesn't make an output, right? Your algorithm should sort the numbers that were given to it, not just produce a sequence of numbers in increasing order. Okay, clearly the running time will depend upon kitne numbers hai, how many elements are there, and quite often it depends upon how sorted these numbers were. If they were already almost sorted, then perhaps your algorithm is not going to take a long time. Of course, it also depends upon what particular algorithm you are using, right? So the running time would depend upon all of these factors. Okay, and the first sorting technique we are going to use is one that you have used very often, right? Let's say when you're playing a game of cards. Okay, so what is the strategy you follow when you are picking up set of cards that have been dealt out to you, right? So you like to keep them in a sorted order in your hand. So you start with your empty hand, you pick up the first card, then you take the next card and you insert it at the appropriate place. So you suppose you have some 5 cards in your hand already, right? Let's say 2, 7, 9, Jack and Queen. Then I get an 8. So I'm going to put it between 7 and 9. That's the right place it has to be in. Yeah. So I am inserting it at the appropriate place, and that's why this technique is called insertion sort. And I keep doing this till I have picked up all the cards and inserted them appropriately in the hand that I have. Okay, great.
Okay, before going further, let's take a short break, and that's your homework 1.1. What we are going to do, just take 5 minutes and try to write the pseudocode for the insertion sort algorithm that Professor Naveen just described. You're free to use if, then, else, while, do, repeat, and all those things, and also English-like language or any native language, and try to write the pseudocode. Do not look at the pseudocode given by him, just try to do it yourself for the 5 minutes, and then we can move on to the lectures. Okay? Why are we doing this? Well, our objective is to make sure that you start actively thinking on your own. And when you submit the assignment, you will not be graded for your efforts, but you will be graded for your efforts, not for the correctness of the code. So don't worry if you cannot write the correct pseudocode. Don't worry, if you don't know how to write pseudocode, just give it a try. And your grading will be based on your efforts, not on the correctness. And just think about it and then try to write some pseudocode for insertion sort. And then in the next 10 minutes, we'll see that how your code is and how is one supposed to write it and how is one supposed to analyze that code and look for its correctness. Okay? So take a fresh piece of paper, spend 5 minutes in trying to write the pseudocode, and then you may continue the lecture. Okay? Okay, great.